And back in the day, you could actually download different programs. So one program I downloaded, so that when my computer kind of went to sleep and it had a screensaver, it was actually computing data for the SETI project, the Search for Extraterrestrial Intelligence. I don't necessarily believe we're being visited by aliens, but I just thought it'd be cool. My computer, if it's not doing anything, why not analyze some data for some people, right? There's another one that was more interesting that was called the cancer fold, the protein folding to try to find a cure for cancer. So if you downloaded the program, every time your computer went to sleep and the screensaver came on, it was actually testing to see if certain compounds would actually fight against cancer. I'm not a biologist, I'm not a medical doctor. I don't know the ins and outs behind what it was doing. I keep doing this because the little animation on the screen would keep rotating. It's really neat. But it was just all this data, and they just need something to calculate it. So finally, to get back to the point we're talking about, there's another app, another background thing you can download that searched for the next biggest prime. So there's a search for the next largest prime. So every time they find a new larger prime number, all the math geeks around the world kind of go, ooh, right? And we take a moment, we sip our favorite beverage, and then we're like, all right, what's the next one? So we know there's an infinite number of them. Here's the thing though, we don't know, let me see if you guys are with me. There's a pattern to like 1, 4, 7, 10, because you just keep adding 3. You guys remember that section about finding a pattern? If you could find a pattern in the prime numbers, you would automatically be the biggest freaking rock star in the world of mathematics. So I tried for a long time to try to see if I could find anything myself. And I kind of like found some stuff that other people had already found, you know, and I'm like, all right, well, I still feel okay because I found it. But nobody has figured out a pattern to the prime numbers. Is everybody sort of with me? And I know that if you weren't in this class right now, you most likely would not be thinking about this. I understand. But are you guys kind of with me? It's kind of neat that we know there's an infinite number of them. We just don't know how to get to the next one. We have no pattern, so we just have to keep coming up with, well, is this one prime? Let's check it. So we have all these supercomputers that are just chunking away and like, okay, it's prime. Oh, cool. And they put out this big release. We found the next biggest prime. Okay. Thank you guys so much. Yeah, I know this guy's geeky. Okay. So let's come back to this here. I want to finish up chapter 5 and then let you guys work on a worksheet. Section 5.1, I think we basically finished it. Yeah, the one last thing I want to say is sort of like what I just said a minute ago. This is on page 184 in case you're somebody likes to follow along in your book. Shit and a half. There we go. Keeps going back. It's okay. So what I said earlier about finding the turnaround point. So for example, if I had 36. Oh, this is good. Jeff, you actually have to connect. All right, give me a second. I was connected earlier. What has happened? Wow. I can't help with that technical difficulty with this. Okay. Now let's just mess with it. So 36. What's the square root of 36? It's exactly 6. So this is going to turn around at the number 6. So if you start making a list of factors, 1 is obviously always one of our numbers, because 1 goes in any answer. 2, 3, 4, 6. And see how 6, if you have a perfect square, you're going to have the number in the middle is going to be paired with itself. 6 times 6 is 36. So now you're at the turnaround point. Now we can start doing our own little rainbow. Right? So now you just got to pair it up with the ones that came before. So 4 times 9, 3 times 12, so forth. 2 times 18. We got 2 commas there just because I wanted to. 1 times 3 is 6 crazy. So I really kind of want that understood. This is the turnaround point because it's the square root of the number I'm looking at. If I can't do the square root perfectly, it's still close to that number is where that happens. Okay. So a little bit later, how later, Jeff? Maybe very soon. Ooh, immediately. Sorry, very excited. Let's talk about how can I tell exactly how many factors I'm going to have in my list. So let's do this with a smaller, wait a minute, 33%? Sorry. Sure. Let's see. Let's do this with a smaller kind of number, just to get used to this. Let's do 18. Can you guys factor 18 for me, like prime factor tree? Make that real quick. Do a prime factor tree. It's not like that look. You want me to do what? Man, poor little dude, why's your battery so? Sorry, little dude. Do this. I'm just gonna have to deal with it. It's okay. So I get 2 times 9, for example. You can do 3 times 6, but no matter what you start off with, you're gonna 2 times 3 squared. Is that cool? If you do 3 times 6, is 3 times 2 times 3, which is 2 times 3 squared. So bear with me. Now, this next part's gonna get kind of nifty. This is you don't really look at numbers like this normally. I need you to understand this. Let me see if you guys understand this on one basic level. So this is 2 times 3 times 3. And if I recombine these, I get other factors of 18. So like 6 times 3 is 18. So any number you break down to its parts, you can recombine them in different ways and figure out other factors. Very often factors that you didn't even think of. Okay. So stay with me. It's going to get a little technical, and then I'm going to make a little shortcut to figure out how. What I want to know is how long would the list of factors be, so I know if I got them all. So 1 is definitely a factor, correct? It's a factor of every damn thing. So if I had no 2's and no 3's, remind me, what is 2 to the 0 power? 1. So that's 1, correct? If I had no 2's and no 3's, I get 1. If I had no 2's and 1 3, I get 3. And if I have no 2's and 2 3's, I get 9. And aren't 1, 3, and 9, aren't they all factors of 18? And if I do 1, 2, and no 3's, 1, 2, and 1, 3, 1, 2, and 2 3's. That's all I can do, because how many do I have to play with? I have 1, 2, and 2 3's. So that's the most I can make. I can only use up to 1, 2, and I can only use up to 2 3's. I need you to understand this. Why does 6 go into 18? Well, another way to think about it is 8's got a 2 and 2 3's, and 6 is a 2 and 1 3. So of course 6 is in 18, because it's using parts of 18. Maybe. We're getting there. We're going to get a nice little shortcut. So this will be 2, this will be 6, and this will be 18. So I ended up with 6 factors of 18. So what is the shortcut, dear God, Jeff? Because I don't want to make that list every damn time, especially if that list is like 45 long. So here's the shortcut. If you prime factor a number, do you notice, do you see how every time I did one of these lines, that didn't sound right, but we're going to move past it? The first number I used was either 2 to the 0 or 2 to the first. Somebody kind of think. And the second line I used was either 3 to the 0, 3 to the first, or 3 squared, yes? Do you guys all agree then the first thing I could have done, I had 2 options, yes? I could either put 2 to the 0 or 2 to the first. The second thing I did, I had 3 options. 3 to the 0, 3 to the first, 3 squared, yes? That is a definition of multiplication. Do you guys agree? So if I prime factor and I see 1, 2, that means I have two options, either 2 to the 0 or 2 to the first. So what's the shortcut, dear God, Jeff? When you prime factor something, add 1 to each power. 1 plus 1, 2 plus 1. This relates to the fact that I had two options for the 2, 2 to the 0, 2 to the first, and I had three options for the 3. 3, 0, 3, 1, 3, 2. So this is 2 times 3, I get 6. And how long was our list? 3, 6. So if you want to know how long the list of factors is going to be, so you make sure that you didn't miss any, especially for the bigger, uglier numbers, this is how you can do it. So here, you guys. Tell me how many factors will, you can do it, Jeff. Yeah, 45. How many factors will it have? I don't care what they are. I just want to know how many will it have. And don't say it out loud. Just go ahead and do it. All right, how does the prime factorization go? Okay, 5 times 9. Now real quick, what if I stopped right there? Doesn't 5 have a first power? Doesn't 9 have a first power? So 1 plus 1 is 2, 1 plus 1 is 2, 2 times 2 is 4. Why is that wrong? Because freaking 9 is not factored all the way, correct? Okay. So you have to get it all the way to the primes for this little shortcut to work. Because then it's all about putting them back together in various different ways you can. It almost feels like we're doing some mad scientist biology shit with numbers. Break it down, put you back together, make me little mutants. So we get 5 times 3 squared. So explain to me real quick, how do I get how many? 1 plus 1 times 2 plus 1. So you get 2 times 3. You get 6 again. Yes. Good job, Jeff. You made one that has the same answer we had earlier. You got very better. What about this? What if I said, how many factors does whatever the hell this number is? How many factors will it have? And I think you guys understand the little trick here. This is kind of a trick question. You don't just do 2 plus 1 times 3 plus 1, right? Why not? Why don't you just do that? Why didn't I stop here? They're not factored out all the way. What is 4? 2 squared. Squared. What's 9? 3 squared cubed. So when I get 2 to the, what do you do with those powers? No matter what you do, you almost can't go wrong. 2 times 2 is 4. Times 3 to the 6. Okay, now do your thing. We would take 4 plus 1 times 6 plus 1. So I get 5 times 7. I have 35 freaking factors in that big ass number. Y'all with me? That would be 16 times 729. Whatever the hell that is. It's huge. So it makes sense it's going to have a lot of factors. I would not make you write out 35 factors for a number. You guys understand? That would be silly. If I did that, you'd have permission to kick me in the shit. Okay. Alright. Is this interesting to anybody? It's okay if it's not. I'm just doing just me. Okay. So 1 part of this is going to be just determining how many factors something has. It might not even ask you what the factors are. But you can figure out how many factors it should have so that when you write the list out, you know you didn't miss anybody. Or you know you didn't create some answer that's not really there. So let me throw 3 letters at you. We've already talked about this in other contexts. Sort of like with distribution, this is undistribution. What does that stand for? Does anybody know? Greatest common factor, kick-ass. And you break down the words, it's the biggest factor, the biggest number that goes into several numbers. So you normally think of it as just involving 2 numbers at a time, but you can actually do as many numbers as you want to. Or as somebody makes you do, I should say. So for example, if I want to do the GCF of, did I give myself an example? Sure. Little tiny one. GCF of 8 and 12. Do you even have to do anything special to figure that out? Can you guys see what the biggest number is that goes into both? 4. Why is 2 not a good enough answer? Because there's a bigger number that goes into both. I like it. So that's where it's interesting. If somebody says 2, you have to explain to them, yes, 2 does go into both, but it's not the biggest thing that goes into both. So 4. So what's the way I can do, so this is 4, this is easy. Real quick, what's 12 minus 8? Interesting. So I'm not saying that is the answer, but somehow if I take the difference, it could be related to what the answer is. We'll talk more about that in a bit. Okay, dropping little teasers for some reason. So what about if I wanted to do this? I got to come up with a better way to do it. Where'd it go, Jeff? We can do that one, sure. There's got to be a better way to do it because, I mean, I can't necessarily see it as easy. Some of you guys might see it, don't say it if you see it. Because it still isn't that terrible, but it's a little bit rougher. So let's talk about the official ways to do this. There's one method called set intersection. I love it, guys. I love when I can see people start taking notes. Can you take a hot minute and write all the factors of 24? And of course, it was done for us earlier in the video, but just make the set of all the factors of 24. And then you can do 40. Now the name gives us away. You don't have to write the full intersection, but just tell me, what would the intersection be between those 2 sets? What's the intersection? No. That's not the intersection. What's the intersection? So again, what's intersection mean? What's the short word for intersection? It's either or and. And you're like, that was so yesterday. Yeah, what's wrong with you, Jeff? Does anybody remember the symbol for intersection? It was either this or this. Which one? The first or the second one is intersection. First one, doesn't look like the letter A that lost its middle bar. So intersection is and. So when I ask you, what's the intersection of 2 sets? You have to tell me every number that is in one and the other one. So just tell me what's in both. What's the intersection? 1, 2, 4, 8. Okay. Now some of you guys knew the answer to the actual question, and I appreciate that. So then, therefore, what does the set intersection method do? Write the intersection of all the factors and then find the biggest one. So you can just jump to that. What's the biggest number that they both have? Freaking 8, Jeff. Dear God. Way to catch up with all of us. I'm sorry. By the way, what is 40 minus 24? Does 16 go into either one of those? Does a factor of 16? Oh, shit. So again, we'll talk more about that later. Somehow the difference of the numbers I'm looking at relates to the possible answer for GCF. It's not the answer, but it relates to it. Oh, then there's another method. So we're going to do the same problem again, another way. And of course, this one's the prime factor method. So just to kind of cut to the chase. Oh man. Oh no. I think it is the network. I love this so much. You're almost dead. I think today I'm gonna go back to the. Yeah, it's okay, Jeff. You'll be all right, Jeff. It's okay. It's all right. Did I bring any paper? No. I sort of do have paper, not really. Oh, here. What's this? Oh, beautiful. I got paper. All right, so I'm gonna go back to the old school way of doing things. I'm gonna let the little ghost redo what I did. Okay. Poor little guy. He's almost dead. Let me see. No, I gotta remember what I was just doing. It was, we were still doing 24 and 40? Yes. Okay. We're gonna do the prime factor method. So GCF, 24 and 40. Prime factor method. So go ahead and, yeah, what I was about to do was cut to the chase. If I prime factor 24, that would be 8 times 3, and 8 is 2 cubed, so I'll get 2 cubed times 3. 40 would be 8 times 5, so it'll be 2 cubed times 5. So maybe not the best numbers for this, but now it's really in your face. Immediately. You don't have to make all these other numbers that don't mean anything. What do they both have? They have 3 2s. They each have 3 2s, correct? So this is not the best example because there's not a lot going on here, which is fine because this is our first little example. But you just write down everything they share, and they share 3 2s. That's all they share, which is 8, which is the same answer we got earlier. Thank God. I like it. Okay. Let's see. Do I want you to do another one? Yeah, let's do another one. What about? Oh yeah. Let's see. Let's do GCF of 90 and no, yeah, 84. So I do it the prime factor method. Oh, looks like somebody crying out. What's 90?
30 times 3.
That's crazy. 30 times 3. And then 30 is 3 times 10. And then I get 3 times 2 times 5 times 3. I get 2 times 3 squared times 5. Oh my God. And then somebody else help me out. What's the first step for 84? What's a good first step for that one? What definitely goes into 84?
2.
Okay, 2. 42. 42 is?
21.
Sure, 21 times 2. 21 is?
73.
Yeah. Okay, so you get 2 squared times 3 times 7. So this is a little more interesting. Just a bit more interesting. They don't each have an immediate chunk that's the same. But start writing what they have in common. Do they both have 2 2s?
No.
So the answer can't have 2 2s. What do they both have though?
3.
They both have a 3. They both have a 2. Do they have anything else?
No.
Nope. And 3 times 2 is? Holy shit. And what's 90 minus 84? Again, Not the answer always, but always related to the answer. All right. Okay. So, here's a little theorem for you. And this is what I keep hinting about. Now, let me ask you this. If two numbers are both divisible by 4, they must both show up in a list of multiples of 4. Does that make sense? So, if you think about, can everybody kind of see in your mind's eye the list of all the multiples of 4? 4, 8, 12, right? Can somebody give me kind of like a big multiple of 4?
400.
400. And somebody else give me another multiple of 4. I don't care what. See? 16? All right. 400 minus 16 is itself a multiple of 4, correct? If I subtract any two multiples of 4, the answer must be a multiple of 4. Does that make any sense? Even if they're the same. What's 8 minus 8? And that's a multiple of 4. 4 times 0. I really want you guys with me. I want it to make sense. The little thing I keep teasing. If I want to know, and this kind of relates, by the way, we're not doing this today. We're not there yet. But you know fractions are coming. Right? It's like when Game of Thrones was good and they kept saying winter was coming. And then it came, it's like, I'm sorry. Fractions are coming. And everything we're talking about right now somehow relates to finding the LCD, which is a big stumbling block for a lot of students, especially when the numbers get gross. So we're actually developing some methods that later I'm going to come back to and say, hey look, we can find an LCD easy now because we did this shit. Okay. So here's my theorem based on what we've been doing. This says if A and B are whole numbers, and A is greater than or equal to B, then the GCF of A and B would be the GCF of B minus A, I'm sorry, A minus B, forgot which way to do this. You write that again. GCF of A minus B. So let's try it out with a couple smaller things. If I'm trying to find the biggest number that goes into two numbers, if I take the difference of the two numbers with one of the numbers, it has the same answer. They would, if there's a number that goes into A and B, they both must be, now stay with me, I think this makes sense. If there is a number that goes into both A and B, a biggest number that goes into both. If 8 goes into both A and B, don't A and B both have to be a multiple of 8? Isn't every multiple of 8 a multiple of 8 apart from each other? Do you guys really understand what I just said? 24 is a multiple of 8, correct? 16 is a multiple of 8. 24 minus 16 is 8, a multiple of 8. Every multiple of 8, if I subtract two multiples of 8, the answer is a multiple of 8.
Yeah.
Think about it. How do I make the multiples of 8? Don't I just start with 8 and keep adding freaking 8? So wouldn't any two numbers be some multiple of 8 apart from each other? If they're in that list? Okay, I really want you guys with me. If the GCF of A and B is some number, then A and B must both be multiples of that number. Which means their difference must also be a multiple of that number. So I love you guys. Now part of you doesn't want to latch onto what I'm saying because you're like, what the shit does this do for anybody, man? So let me show an example, concrete example about how this makes finding GCFs easier, especially when the freaking numbers I give you are huge. So what if I gave you, what did I pick? Yeah. What if I said, find the GCF, maybe I'll let you see what I'm writing, of, where'd you go? There you are. 880 and 275. How do you guys feel about that? It's okay, be honest. Would you be excited to see the problem?
I agree with you. That's okay. Hey, look at us. I love math, and I don't want to do that, but because that would suck. Can you imagine prime factoring 880? Can you imagine making a list of all the factors? Do you want to do that? Shit, no. So instead, if there is, I really want this to make sense. If there is a GCF for both of those, they both must be a multiple of that. That's almost too silly to say. You guys, that's what that means. Are you guys with me? If 5 goes into both, they're both a multiple of 5. If they're both a multiple of 5, then the difference of them must also be a multiple of 5. So I can make my question easier in steps just by continuing to subtract. Now, dear God, does it make sense I want to subtract the smaller from the bigger one? Okay. I love you guys. Thank you for tolerating me. Some of you guys look like, please let this one. All right. What is 880 minus 275? Whoa. Zoom out a bit. I got used to this thing again. Come back to me. Do I have to borrow an in? So it's 6. Well, I have to borrow a little bit. 05. Right? It's easy. 5 makes 75, 80, and then 6 makes 200, 800. Bam. You with me? So far I know this is equal to the GCF of 605 and 275. Because again, whatever the answer is, they must both be multiples of that thing, and if I subtract them, the answer is still a multiple of that thing. This is still gross, but do you see if I keep doing it, it's going to become a lot less gross pretty quickly. So if I subtract 275 again, what do I get? Watch this trick. 30 would make it 05, right? 30 would make that 105, and I need to make that, so that'll be 330. 300 and 200 would be 500. 30 and 75 would be 105, so that makes 605. Or you want to come. So that's the GCF of 330 and 275. So don't worry. I really hope you guys get a feel for why this works. Can you imagine I could have really big ass numbers and this subtraction would take for frickin' ever, correct? Okay. So please be aware. I've done this enough where I'm like, okay, there's a shortcut, right? So you know I'm not going to make you subtract 275 83 times on a test. Okay. Because of course we already know what the answer is. But I'm going to continue this one and then we'll do a shortcut. Subtract 275 again. What do we get? We get 55. Now I turn around. Now I check. So the answer to this is the same as the answer to this. Is everybody with me? And up here, why did I start subtracting 275? Because the other number was freaking bigger. Now what do? Yeah, 275 minus 55, right? Now let's be smart about this. What is repeated subtraction? Division. So I'm not going to quite get there yet, but couldn't I subtract 2 55s at a time instead of 1? You guys, what's 2 55s make? 2 55s is 110. So let me subtract 110. I get 165. There you go, Jeff. Let me subtract 110 again, and I get 55. You with me? So this becomes the GCF of 55, 55, and the answer to that, what's the biggest number 55 has in common with 55? 55. Okay. Sorry. Okay. So from the beginning, let's see what the ultimate best shortcut would be. Because we know that repeated subtraction is division. And the whole process this is built on is repeated subtraction. So from the beginning, what we could have done. You guys have your calculators ready? What do you get when you do 880 divided by 275? 3.2 exactly?
Yeah.
Okay. Now what's 3 times 275?
What did you ask?
What's 3 times 275? 825. So now I can see what the remainder is. What's 880 minus 825? So real quick, y'all, if you do it in the calculator, you're gonna get 3.2. And I'll remind you about a shortcut I showed you earlier. Please be with me. I know there's a lot of kind of math. The math isn't hard, but there's a lot of it. Sort of like happening suddenly. How many times did we subtract 275 up here before we had to kind of like do something different? 3 freaking times. And how much was left at the end of subtracting 3 times? Freaking 55. So, I mean, if I do 3 repeated subtractions, I'm left with what remains. He who remains is 55. So this is the same math work. We're just doing it more efficiently. Division makes repeated subtraction more efficient. Just to remind you, this is not necessary for you to understand. But can somebody do 0.2 times 275 for me? Wasn't that the decimal remainder we had? What's 0.2 times 275? 55! Okay, sorry, I'll stop. Sorry. I'm a little loopy. Okay. Alright, whatever, John. And so we got this so far. So this equals this, and then I can just divide 275 by 55, and what do you actually get? Yeah, you get 5. Remainder what? 0. I love it. You look at me like, what do you want from me? No remainder, correct? So that means this is the GCF. If you do this repeated subtraction, when you do division as a shortcut to repeated subtraction, you know you're done when you get 0 remainder. You know what you just divided by is the answer. I love you guys. Because if I would have done one more subtraction here, wouldn't I have gotten 55 minus 55 is 0? Okay. Maybe. Do I want to go back and do that? No. Okay. Oh yeah, that's right. So if I want to capture what we just did, if A and B are whole numbers, A greater than or equal to B, and A equals, oh God, here we go everybody, BQ plus R. So be like 880 is 3 times 275 plus 55. R is the remainder. Q is the quotient. A and B are what I'm dividing. Yeah? Then, the GCF of AB equals the GCF of RB. And whenever you write it with nothing but letters, you lose what the shit we just did. But didn't we just figure out that 880, 225 was equal to 55, 270? What was 55 again? It was the remainder. So wouldn't this be R comma that thing? So the GCF of two things, when you divide it and you get a remainder, it becomes the remainder with the other dude. Just like it did here, remainder with the other dude. I love you guys. So remember, I think you all were with me about the subtraction thing. Division is repeated subtraction. It just makes a shortcut out of it. So the idea hasn't changed. I'm just subtracting quicker when I do division. Okay. And again, I've got a little handout. You guys will be able to practice some of this here in a bit. What do you think I'm going to talk about next? That's GCF. I haven't done anything, so all of a sudden I'm going to do a Roman numeral 3. 3,000. That's okay. Yeah, LCM. And LCM stands for least common multiple. Of course, multiple means What's a multiple of 6? Give me a multiple of 6. 12. Okay, so multiple meaning a number you can multiply up to b. So our brains very often clue in on the word least, and we think it means to factor because it's making it smaller. But this is the least common multiple. The smallest number both numbers can multiply up to b. If I put them on the denominator, this becomes LCD. So LCM and LCD are the same damn thing. So again, we have several different methods. So if I want to do an example, Jeff, holy shit. If I want to do the LCM 15 and 20. The most basic way that people do this is to start just making multiples and see where they meet, right? So that would actually be the set intersect the set intersection method. Same idea as we did before, right? The set intersection method. Make a list of multiples of 15. Make a list of multiples of 20. And we already see what we're gonna do here, yes? When I'm doing GCF, it's the biggest number they have in common. LCM, smallest number they have in common. Okay, I like it. And again, some of you guys are used to this, because I think this is the way some of you guys do LCD. Is just start building them up and see where they meet. Okay. So what about, what's the next method we did earlier?
Prime factor.
Holy shit. All right, so I can do prime factorization. So if I take 15 and 20, this is 3 times 5. This is 2 squared times 5. Is that cool? Right, 15 is 3 times 5, 20 is 4 times 5, which is 2 times 2 times 5. So earlier, when we did this, we had to write down the smallest thing they all had in common. I mean, I'm sorry, the most they had in common. Here I want to write down everybody. I want this to make sense. The LCM, doesn't it have to have 15 and 20 in it? It's got to be something that both multiply up to b, right? So it has to be the smallest number that has both 15 and 20 in it. Does 15 times 20 have 15 and 20 in it? Well, yes, Jeff. Yes, it does, because you put them both in it. Why is it not the smallest thing? Because that's repeating some shit. If I just multiply everything together, aren't I repeating the 5? So here's one way to do this. Here's how to do it straight from the prime factor tree. My LCM must have everything that's here, but no more than what's here. So it's got to have a 3 and it's got to have a 5, correct? Now you look at this dude and you say, what does he add that's new? Is the 2 squared new? I didn't have that yet. Is the 5 new? I got one of those. I don't need one of those. Yeah? And help me out. This is 4 times 15, which is, or 10 times 6. 60. Same answer we got earlier. Yay. Okay. So then there's a third way to do this one. Why am I slow with that? This one's more the way I show it for fractions. So maybe, no, I'm not going to do that one. Yeah, I will. Screw it. I'm going to do fractions. So I lied to you earlier. So if I have to add those together, and I'm pretty much going to always be very careful to say, find the LCD. Because really, technically, I just have to make the bottoms the same. Now let me just have a quick word because I'm throwing the fractions at you. What is x plus x? No. What does exponent mean? What operation does exponents mean? Multiplication. X plus x. 2x. Coefficients, repeated addition. Exponents, repeated multiplication. What's x plus y? X plus y. I love it. You're like, you already said the answer, Jeff. Oh yeah. So when I'm trying to add 1/5 plus 2/5, right? Getting past the factor sounds like I have a list. 1/5 plus 2/5 is like 1x plus 2x. They're like terms. So adding fractions is just the idea of like terms. Right now I've got 1/15 plus 1/20. Are those like terms? No. If it was 1/15 plus 1/15, that'd be freaking 2/15. Because I got two of the damn things, right? But here I got one this and one that. So I've kind of, so x plus y. Can we do shit to make those, I can erase the little thing and make x look like y, but that's not really allowed. You guys with me? But here, they're numbers. I can do something. So, this method is called the build-up method. Build-up. So 15 is 3 times 5. 20 is 2 squared times 5. And I kind of relate this to, if you have kids, or if you've ever been around kids, or if you ever work with kids, and you're giving them ice cream, and one kid gets a little more ice cream than another, what's going to happen? Or one kid gets ice cream, and the other gets ice cream with sprinkles on it, what's going to happen? Shit going to go down, right? It's not going to be pretty. You guys with me? And this is probably good when I don't have kids, because I just eat all the ice cream and go, I get it all. So if you look at the first kid, is the 15. He's got a 3 and a 5. Does he see something the other kid's got that he wants? Does the other kid have something that he doesn't have? Yeah, what's the other kid got? The other number. 2 squared. He's got 2 squared. That's not fair. So to make the kid happy, I'm going to give him sprinkles. I'm going to give him 2 squared. And the only way to make it legal is to do it on the top also, right? Now what's this kid? Is this kid happy at the moment? So again, I gave the top and bottom a 2 squared because now they both have a 2 squared. What's this kid still upset about? This kid's got a little freaking vanilla wafer in there and he's like, what the shit, man? So I'm going to give him, now are they both relatively happy? Okay, I like it. And of course, what is that denominator now? Isn't it the same thing we just got up here? So these methods are basically the same in a way, except this is a little more in your face. I'm giving each thing what they're missing. Whereas this one is, I'm building the answer by just taking each thing, just one of each thing. Not one of each thing, but like, I need a 3, I need a 5, I need a 2 squared, I already got a 5. That approach. I get the same answer. I better, because there's supposed to be a different method to get the same thing. You guys remember seeing this kind of thing? I know you've all worked with LCM, you all work with GCF, but who knows what methods you use to get them. You've never seen it? Okay. Does it make sense? Okay. That's more important than if you've ever seen it. I'm sorry guys, I'm almost there. Ooh, there's only one sheet of notes left and then I'm gonna shut up, okay? You're not gonna leave, we're gonna do a worksheet, but at least I'm gonna shut up. So help me out, let's see this. So if I give you this number, and this number, sorry, let me actually show you what I'm dealing with here. Okay. If I multiply all the crap out, I'm going to get 2 numbers up there, correct? So I want to know the LCM of those 2 numbers. How would you build that? I want to show you a shortcut. If you've got it all prime factored out, there's a beautiful kind of shortcut way to remember this. So look at the first dude. What does my LCM have to have in it? It has to have both of those in it. So how many 2's must my answer have? 5. Why is 3 not enough? Doesn't the other guy have 3? Why is that not enough? Because the first dude's got 5. You guys kind of with me? Would I give it any more 2's? If I have 5 2's, don't I already have 3 2's? Because I got 5 freaking 2's. I'm like swimming in 2's. All right. So the shortcut for LCM, if you got it prime factored, let me say that sentence again. The shortcut for LCM, if you got them all prime factored, is you take all the highest powers. Yeah? You guys see some other thing now? You take all the highest powers. Because you just told me you're going to take 5 2's, not 3. And the reason you used will be the same for each freaking number I see. So how many 2's will be in the answer? We already know. 5. How many 3's will be in the answer? 3. How many 5's will be in the answer? 1. How many 11's will be in the answer?
2.
And how many 17's will be in the answer? 1. Okay. And then whatever the hell that is, I am not going to try to multiply that in my head. I refuse. You guys can do it if you want to. So what about GCF then? So LCM is biggest power on each. And I really want this to make sense. Can you find all of these numbers in there? You can find 3 2's, yes? You can find 3 3's, you can find 2 11's, you can find a 17. Can you find all of these numbers in there? Yes! So that's why it's the LCM. Isn't the LCM supposed to be the number that has both numbers in it? What about GCF? Now I'm talking about what they have in common. How many 2's do they have in common, for example? Do they have 5 2's in common? No. So how many 2's do they have in common? 3. So therefore, the shortcut for GCF is lowest power on each. Oh my God, that kicks ass. Whenever there's an analogous kind of approach, LCM is the biggest power. GCF is the lowest power. So how many 2's? 3. How many 3's? 2. How many 5's? 1. No. Careful. How many 5's are over here? None. No 5's. How many 11's? 2. How many 17's? None. Because if I ask you how many 5's do they have in common? 0. Oh, I'm sorry. Should be a 3. Okay. So you can tell how, I really want you to see how this is kind of nice. Lowest power on each. And what that really means, help me out, just to remind you guys. And if you want to, you can write this, and if you don't want to, you never have to. How many 17's are here?
0.
So isn't this 17 to the 0? Because anything to the 0 is 1. So if you wanted to, I don't see why you would want to be honest, but this will remind you, oh, the lowest power is frickin' 0, so I got no 17's down here. Or you can just say, I don't see any 17's in that dude, so I got no 17's. Now, this shortcut comes with confusion because least common multiple, biggest power, greatest common factor, smallest power. Yes? It's understandable that it's confusing. But hopefully you guys saw why it works that way. Okay. LCM is all about building up. GCF is all about tearing down into parts. Okay. There's a really cool little thing, though, I want to show you. Why is this a relatively easy problem? What's the LCD? Bless you. Bless you. Bless you. 15, right? Because they're each missing each other. Why is this one more complicated, Jeff? Is the LCD 560? Do you see where I got 560? Yes. Isn't the LCD here 15? Do you see if you do too many examples like this, a kid's going to think the LCD is always just multiply the damn things together? So why is the LCD of this so easy, but the LCD of this is harder? Because 3 and 5, do they share any factors? No. 8 and 70, do they share any factors? Yes. So this is kind of cool. I desperately want you to be with me on this. What's 8 times 70? 560. What is the GCF of 8 and 70? This isn't too bad because 8's only made up of 2's, correct? So how many times can you divide 70 by 2? Once. So 2 is the GCF. 8's only got 2's. So the GCF could either be 2, 4, or 8. Or 1. What's 560 divided by 2? 280. That's the GCF. I'm sorry, that's the LCD. There it is, Jeff. So if you multiply the bottoms together and then divide by the biggest factor, you get the LCD. You get the LCM for us for right now. Love you guys. That's actually the way I do that kind of thing, to be honest. If I need the LCD, I multiply and then I divide by the biggest factor they have. So here's, if I want to formalize this thing, the LCM of two numbers is equal to A times B divided by the GCF of the two numbers. That is a very useful little fact. And this is trying to be a little time simple. I always forget I can use X for times for us. Now, I'm not going to spend a ton of time on this, but I just want to point this out in case anybody reads this. The book is wrong, which makes me concerned. What really makes me concerned is I didn't notice until now. First off, I should have told you it was wrong. I should have let you read this, but that's a little evil, because then I'll say, it's wrong what you just read. So there's the infinite number of primes, yes? Come back to me. Thank you. There's an infinite number of primes. And they say, let me see if this makes sense to you guys. What is 2 times 3? Therefore 6 is not prime. Yes? But if I add 1 to 6, I get 7. 7 is not divisible by 2, and is not divisible by 3, because it's 1 away from a multiple of 2 and 3, correct? So, on the surface, I really want you guys to look at me. On the surface, this kind of idea makes sense. If I multiply every prime number I know and then add 1, it's understandable why you would think that must be a prime also. So if you do 2 times 3 times 5 times 7 times 11 plus 1, 2 doesn't go into it, 3 doesn't go into it. Are you guys at all with me? If I take a multiple of 3 and add 1 to it, can 3 go into that number? Ain't no freaking way in hell, because every multiple of 3 has to be 3 apart, correct? So on the surface, this makes sense. But this is so wrong. Has somebody got a calculator? You got a calculator? Anybody? Got a calculator? What is 2? Help me out. What's the next prime number?
3.
3, next one?
5.
5, next one?
7.
7, next one? 11, next one?
13.
Okay, do that. Do 2 times 3 times 5 times 7 times 11 times 13. 30,030. Now add 1 and you get 30,031. Now the book would say that's prime, and the book would be wrong, guys. And you're all like, I want my money back. Divide that by 59, I think it was? Yes, divide that by 59. And you get 509. Is that prime? Shit, no. So the problem with this, was it Euclid or Euler? One of the E people. He kind of came up with this idea, and he said some of these will be prime. When I multiply a bunch of primes together and add 1, I'm getting a very large number. it could be divisible by a prime bigger than any prime I thought of. I need to say this again. That number is definitely not divisible by 2, 3, 5, 7, 11, or 13. Because it's one away from a multiple of any of those. Do you guys all agree with me that 2 times 3 times 5 times 7 times 11 times 13 is a multiple of 11?
Yeah.
Because it's 11 times shit. So isn't that number a multiple of every single thing in it? So if I add 1 to it, it's one away from a multiple of any of those, so none of those go into the answer when I add 1 to it. None of them can go into it. If I added 2, then 2 would go into it, because now 2 goes into both parts. Okay, maybe. So you can understand why somebody might think, well, then that seems like it's prime then. But are those all the primes? When I multiply and get up pretty big, maybe a larger prime number goes in, like 59. That goes in. Because I didn't think, oh shit. So, all right, I'm sorry. I made a big deal out of something you probably don't quite fully understand it. But it gets me a little irked that this part of the book is wrong. But I just want to let you know. So here's the part I promised you would happen. I'm going to let you guys work. I think I want to do a little different today. I want you to work on this a little bit by yourself first, and then I'm going to put you together with other people. So try not to talk to anybody as you try to do these. All right, guys, I know you're not quite done. And again, it seems like I'm going to go ahead anyway. A and B sound they're the exact same question, basically, right? But the idea is one that's come up before, and I'm pretty sure I used this term before, relatively prime. Relative to each other, are they prime? So, is 4 prime? Is 4 prime? Hell no. Is it relatively prime to 3? Do 4 and 3 share anything? Any factors? Beyond 1. Everybody shares 1. Nope. So 4 and 3 are relatively prime. So if 3 is a factor of a number, and 4 is also a factor of the number, does 12 have to be a factor of the number? Yes, of course. Yes. In fact, what's the rule for determining if 6 goes into something? What do you have to do for number 2? When do you know 6 goes into a number?
2 and 3 relatively.
Because if 2 and 3 go in, if 2 works and 3 works, then 6 must also work. That's basically what part A is saying. Why does it work though? Because 3 and 4 are relatively prime. You cannot come up with a number that 3 goes into it and 4 goes into it where a 12 does not go into it. How would you come up with a number that has 3 in it and 4 in it? What would you do? Well, the most easiest one you could do is freaking 12, right? 3 times 4 is 12. Couldn't you then also do like 3 times 4 times 11? 3 squared times 5 times 4. I want you to be with me. If I wanted to construct a number that has a 3 and a 4 in it, don't you have a 3 and a 4 in it? Meaning you have a 12 in it, yes? Can't do the 12 fingers because I'm not like that. Part B is different. If I tell you 6 divides a number, doesn't that mean that 3 divides the freaking number? So when I say 3 divides it, did I give you more information? No. If I tell you 6 divides into a number, doesn't that mean that 3 goes into it? So when I say, oh, you have 3, I'm like, you didn't give me any more information. So it doesn't like go together the way that part A does, because 3 and 4 are distinct pieces of information. So here's an easy way to do this. What's the smallest number that 6 goes into? 6. If I let A be 6, does 3 go into 6? Does 6 go into 6? Does 18 go into 6? Does 18 go into 6 even? Nope. So if 6 goes in, I want this to make sense. So the first problem says, I have a number, and the number has a 3 in it, and it has a 4 in it. And it might have other shit too, but it definitely has a 12 in it, yes? This one says, the number has a 6 in it, and it's got a 3 in it. Doesn't it already have a 3 in it when I wrote the 6? So does it have to have a 18 in it? Nope. Okay, maybe. So if they are relatively prime, if I know that one and the other go in, then the multiple of those go in. That's where we got the rule for 6. If they're not relatively prime, I don't know shit. I don't know that the multiple goes in also. So how do we determine if something's divisible by 15? If it meets the rule for 3 and it meets the rule for 5. That would mean 15 goes in, because 3 and 5 are relatively prime. Is the rule for 12 that 2 goes in and 6 goes in? No, because 2 and 6 are not relatively prime. Maybe. Is this obvious shit I'm saying right now? No. So get off your own back. If it's not immediately making sense, you got to work with it a little bit. Yes?
So to provide a counter example, can't you just use A?
Do what?
To provide a counter example, because it says like if it's false, would you just provide one that like is like A? Or like how would you?
Well, like I said, to do a counterexample, you pick a number that these work for, but this doesn't. So a counterexample's got to show that this is true, but it doesn't lead to this. It is impossible to find a counterexample to this, but it is very easy to find a counterexample to this. So if I pick A to be 6, this is true, this is true, this is not true. And again, be very careful. 18 does not divide 6, but 6 divides 18. So when I say does 18 divide 6, the answer is no. It does not go in evenly. What about part C? Do you see how C is different? 2 goes into one number and 3 goes into a whole other number. Now real quick, can you guys help me out? If 2 goes into a number, M, what does it mean is true about M? It's even. So to get a little more specific, M's got to be 2 times something. Is that cool? If 2 goes into M, M must be 2 times something, correct? If 3 goes into N, N must be 3 times something, yes? Let me stop for a minute. You can immediately rewrite. You can immediately, if I tell you this, you can immediately write this. Will it always be helpful to write that? No. Will it sometimes be helpful to write that? Shit, yes. What's the last thing you want me to investigate? Does 6 go into N times M? Do I have an expression for N? Do I have an expression for M? What is N times M? 6AB. So is 6 in there? In your face. So that's true. So it's really good to remember what the divisibility means. How can I rewrite it? And trust me, the hardest part about any math class is proofs, which is basically what this is, a little baby proof. So N times M equals 6AB, and 6 is obviously in it, therefore this is true. Okay, I like it. Ooh, I actually kept you the whole time for once. Yeah, we're let out 220, right? Yes. All right, we'll finish this up next time, guys. Thank you for indulging.
Yeah, we're gonna be saying that.
Oh, practice it, yeah. Thank you. You good? right, guys, I'll see y'all Thursday. Oh, I'm sorry. You're good.
Thank you.
Everybody got a practice test, yes? Okay.
Gave you an extra.
Oh, that's what happened. Okay, thank you.